Welcome. You are about to view a recorded talk of the Mathematical Consciousness Science online seminar series. This seminar series aims to explore the role of mathematics in the scientific study of consciousness and hopes to connect researchers who have an interest in this topic. While every session of the seminar consists of a talk and discussions, the latter are not recorded and the following will only contain the talk. We hope you will enjoy it. For further information, please visit our website, seminar.math-consciousness.org.
Thanks so much. I really appreciate the invitation and the opportunity to discuss this stuff. This is new work in progress, although there is a publication. This is the paper. My co-authors, Oren Kolodny, who is at the Hebrew University, and Roy Moyal, who is here at Cornell. And what we were after was to explain, perhaps, the evolutionary function of the phenomenal conscious experience of pain. Of course, this is a perennial question: why does pain hurt? The question why, usually in a setting of complex systems or biology or evolution, has many meanings, and we were after specifically the functional meaning, although we can discuss, and I will try to touch on the broader aspects or various more difficult kinds of the why question that apply here. But specifically for now, what is the function of hurting? What might be the function of hurting? As opposed to what could be the alternative? Well, an alternative is depicted here. This is smoke detector, a typical domestic smoke detector, and there is a smoke detector principle out there promoted by various researchers who study pain. In a recent review, Nessie and Shulkin proposed that principle as an explanation for one thing, the kind of pain that seems to be overzealous. And why should we feel so much pain for a reason that seems minor? Well, the smoke detector principle is that it's better to err on the side of a false alarm than missing the actual fire. But an important point, in fact, the key point here is, could the hurting aspect, the felt aspect of pain, be purely informational, like raising an alarm? After all, when an alarm sounds or goes off, I really don't believe that the system that it is connected to or the alarm itself feels any pain. So it's purely informational. And that's a key question. And one can also ask, what if evolution were in the play? Of course, evolution, as we know it, was not in the play in the construction of this alarm, but in our pain, nothing in biology makes sense except in the light of evolution. So we all know that phrase, Theodosius Dobzhansky saying, and it's really true. So how does evolution play into this picture? In that review, which I mentioned, Nessie and Shulkin conclude very clearly, unequivocally, several times, different paraphrases, that pain has a clear evolutionary basis. But what I would like to know is, what about hurting? Because this argument works for informational pain. It's definitely better, and it's probably evolutionarily worth knowing that there is a fire somewhere in the body than not knowing it. But that's just knowledge, that's just information. Why do we have to hurt in addition to knowing that something is wrong? Thomas Metzinger, one of my favorite philosophers and scientists who study consciousness, in a recent paper suggested that suffering, which is kind of a big brother of pain, pain plus loss of control, must have another role or a broader role than just serving a distress signal. He wrote that, functionally speaking, suffering is necessary for autonomous self-motivation and the emergence of truly intelligent behavior. And I actually emphatically agree with that, but I really would like to have an explanation. I need this explained to me, how exactly this works in evolution. In particular, one maybe minor comment relative to the big picture of evolution, but still, I think, a valid question: why does autonomous zombie-like AI seem to work? Consider a self-driving car, and self-driving cars learn to drive pretty well, maybe not perfectly, without ever experiencing pain, or at least one hopes for the sake of all those Teslas on the road, that they do not experience pain. But we can ask, kind of doubting the doubt, we can ask just how well a car can learn, how far can it go in learning to drive without experiencing pain. This image, I think it's a fake situation. It doesn't seem to be a real one, but it stands to reason that if you draw a line like that around a car trained in the United States, it would be trapped inside, because it has a rule not to cross a solid white line. That brings to mind the possibility, an idea, instead of marking a solid white line as impassable, maybe it should be made just painful to cross, and then the car's ability to cross a solid white line would depend on circumstances, maybe on that particular car's tolerance for pain. And let me appeal to you, to your common sense. Wouldn't you be prepared to tolerate some pain if there were a good reason for doing so? Just remember your last visit to the dentist, that kind of stuff. And I think you would be answering me in the affirmative. So perhaps pain is an evolutionary win. But that merely puts the focus on the question, on the computational question, I guess. One of the aspects is computational. What role could pain play in reinforcement learning and in decision making? And remember, evolution lurks in the background here, as it does everywhere. So here's a classic depiction of a framework, an architectural framework for intrinsically motivated reinforcement learning. This is from a book chapter by Andrew Barto. It's pretty universally accepted now in the machine learning community, also among psychologists and biologists who study this kind of learning, that the rewards are internal to the system. So you can see here, the external environment may provide sensations, and of course it takes the actions of an agent, but the critique, the reward, positive or negative, comes from within. And so the critic is part of this internal environment, and the agent that decides what to do, where to go from the present state to the next state, is evaluated by the critic. What went without saying in this diagram, and something that I want to bring out explicitly, is that this reinforcement learning agent actually has an internal computational structure. The agent is a collection of actors, each with an agenda, and that gives rise to some interesting issues, which I think might point to a solution to the question that we've posed in this paper. So consider that much older diagram from Oliver Selfridge's famous paper on the Pandemonium, 1959. You have the cognitive demons. These are our actors, the decision demon that listens to them and picks the one that shouts the loudest. And on the basis of that, it makes the decision. So if we want to add learning to this picture, this is how we can do it. Remembering that intrinsically motivated reinforcement learning scheme. So now we have the outcome, which is evaluated by the critic internal to the system. The critic may compare the outcome to the plan, and then there is feedback to the agents, to the actors, that allows them to learn. In fact, the modification of the parameters here constitutes learning. So there is a problem, though, here. And the problem is, how can the actors be trusted? This illustration, a version of the Pandemonium, a very famous one from a wonderful, wonderful textbook by Lindsay and Norman, which came out in 1972, still very readable, very much to the point. Here's a pandemonium with the demons depicted as screaming. And if the demons, so imagine if the actors' existence, continued existence, depends on their participation in the process of decision-making and learning, the actors would be intrinsically motivated to stay alive and maybe to shout the loudest. so as to be noticed by the decision demon. And in fact, this is not unlike the situation in developing nervous systems, which in many cases come online with many, many more neurons that we actually need in the adult stage, and the neurons that do not contribute enough or contribute less than others are called. So agents have, each actor has an interest not to be called. And so this promotes, or you would assume, stands to reason, this would promote agents' behavior or actors' behavior, which cannot be trusted because of this self-interest on part of the different agents. Remember, there are multiple actors in each such learning system. So trusting the actors, thorny issue. Here's a situation that we can use as an example: some juicy blackberries, which we would like to reach for and pluck and eat, but there are thorns. And maybe there is actor number one that pushes for approaching the bush, despite the brambles and everything, and another actor might promote avoidance. So should A1 be trusted, or should A2 be trusted? How would we arbitrate, or who would in fact arbitrate this decision, and how? So the handicap principle to the rescue, an evolutionary principle that has been put forward by Amot Zahavi, late of Tel Aviv University zoologist. This idea, the handicap principle, has been referred to as the greatest advance in evolution since Darwin. And if this is the first time you hear about it, I kind of envy you, because it's quite an eye-opener, and it's being hotly debated and yet accepted in some form or another. And let me use this illustration, one of the first that Zahavi himself came up with to introduce this. So here's a cheetah observing a herd of springbok, and let's see what happens.
So they must get close. But springbok have keen senses. True to their name, springbok can leap 2 meters high. It's jumping with a purpose. It signals a warning to the others and confuses attackers.
So the BBC narrator for once misses probably the biggest point of this jumping in place or stotting on part of the springbok. Perhaps the most important function, evolutionary function, of this weird behavior is communicative, and it constitutes a signaling attempt on part of the springbok, on part of the antelope, to the effect, I have high fitness, I can jump in the air, which is very costly in energetic terms, despite being pursued. And so it's not worth your while, dear cheetah, to pursue me, pursue the others who do not jump as high. So if this communication attempt succeeds, that's definitely good for the particular springbok in question. And the interesting aspect of this type of communication is that honesty is enforced here. So a springbok that would like to lie here cannot, because this is costly signaling. It costs to jump in the air like that. So the handicap principle has been linked and transformed into this big subfield in evolutionary biology, in zoology, in ethology, which is called honest signaling. This collection of illustrations is from a recent review by Lerder and Johnstone. On the left top is probably the most famous example. The peacock, the huge tail, of course, is a costly display. You can't fake it. You have to grow it, investing resources and kind of weakening you. And so when the peacock flaunts its tail as a display of fitness, it cannot be lying to the extent that the display is costly. So honest signaling, we can invoke it here, and that's a key point in this paper. Let me just quote the price of participation on part of the actors. So think again about this scheme in which actors vie for access to the control of behavior. The price of participation is raised such that only the better off actors can afford it, and actors bid to meet the cost of participation is thus a signal in the classical sense that both sides stand to gain by using it. So the notion of signal is not trivial in zoology and mythology, that this is how signals usually are defined. Both sides stand to gain by using it, but only if the signal is honest. And the honesty of signaling in this scenario is underwritten by the bidding process. Actors can only gain access to output control by paying upfront a cost which is imposed on all the actors, and which the overconfident ones can, in the long run, ill afford. And that cost is experienced by the system as pain. So this is not an explanation for all types of pain. This is an attempted explanation for one particular functional evolutionary reason for there to be the hurting aspect to pain. And returning to the example of brambles and berries, the pandemonium augmented with honest signaling of the actor's confidence essentially asks itself, am I sure it's worth the pain? Where the I here is a composite entity. It's all the actors plus the critic. Sure it's worth the pain. Put your money where your mouth is. That's the principle in action here. So let me offer an example from neuroscience, which I found when I first was pointed to it by my colleague, my co-author Oren, quite surprising. Note that Zahavi, the initiator of the Handicap Principle, is a co-author here. Why are neurotransmitters neurotoxic? An evolutionary perspective. This is a figure from an old paper which shows glutamate. So GLU is glutamate, a particular kind of synapse in which glutamate serves as the signaling agent substance released from the axon terminal, percolating, diffusing to the dendritic spine. So the point here is that it turns out that glutamate is neurotoxic. Too much glutamate kills neurons. This is like, imagine if too much speech would kill you. So you kind of really save what you have to say for a special opportunity, because if you talk too much, you die. This is the essence of the situation here. And an honest signaling explanation, I think, works wonderfully here, because neurons are kept honest in the sense that I described by the toxicity of the neurotransmitter that's involved here. Switching gears again, where could those actors, the pandemonium actors, be in the brain? So we have singled out a very well-known circuit, the basal ganglia-thalamus-cortex loops. This may not be saying much to everyone in the audience, but let me just describe it on a very high level as one of those pieces of brain circuitry where you can almost discern an engineering reason kind of peeking through the actual wiring. There are loops, as the name of this subsystem says, that run through some of the older, maybe the oldest parts of the vertebrate brain, through to the newer ones, cortex, if you have one, if you're sufficiently evolved to have one. This is a very strongly conserved brain circuit. You can see from the diagram on the low left, if you can discern, the font is a bit small, the lamprey, whose line diverged from ours, in fact, from all the jawed vertebrates about over 500 million years ago. This lamprey, it's not a nice picture. Let me make it go away. The lamprey has this circuit. We have this circuits, and the fish have it, amphibians, reptiles, birds, mammals. We all have this circuit. So it's thought to be extremely central and indispensable to behavioral control. In fact, the basal ganglia, the brain structure that is part of this circuit, is the way station for, in animals like ourselves, in mammals, is a way station for the motor outputs. If you thought that your motor cortex really controls your muscles, it has to go through a way station where the selection of actually pre-compiled, if you wish, actions is available, and a decision can be made as to which of the actors, to use the terms from the Pandemonium, which of the actors should be given access to the current output. Here's a diagram of those loops. As everything about the brain, things are a bit more complicated than you thought they are. It's not just simple loops. They branch and they recombine, but basically what you can discern here, and my message intended in this slide, is that there are divisions. The loops are many, maybe three or four or five major groups of wires, so to speak, running in parallel, making stops at various way stations. And the separation of those circuits which run in parallel roughly corresponds to the separation, at least on the motor side of things here, somatic sensory motor, roughly corresponds to the choice of actuators. So again, this is, to my mind, amazingly close to a scheme in which multiple actors kind of are competing, run in parallel, and whose circuits run in parallel through large parts of brains like ours. And action selection, this is from a recent paper in which I think optogenetic control was being exercised by making things happen at one of the way stations in the circuit here in the striatum. And when one subset of those neurons is activated, the animal, in this case the mouse, goes into one kind of behavior, and a different subset of neurons here launches a different kind of behavior. And those behaviors are, in this case, in the case of mouse here, are preset, they are precompiled, they need to be chosen, and they compete, the advocates for each of them compete with each other, and there is excitation and inhibition in those circuits, and action selection happens, and the mouse settles for the next few seconds to do this or that. So here's the interim summary then. We asked two questions in this paper, and here are the questions and the answers we offer. What is the functional evolutionary reason because of which pain is felt and not merely informational? And so the reason we propose, the evolutionary function of pain, is in providing an additional independently effective basis for action selection that is orthogonal to the outcome-based reward that drives standard reinforcement learning. Now, this is important for it to be orthogonal, because if it's just another kind of reward, pain would be purely informational, and it would be subsumed in the general standard scheme of reinforcement learning. It has to do something that's functionally orthogonal to the standard positive or negative reward. And what's the computational mechanism through which pain fulfills this function? It's a variant, as we saw, on an actor-critic architecture, in which the cost of bidding on an action differentially affects the confidence account balance of the participating actors. So the rich or higher balance actors are better positioned to meet this cost, which is upfront, and this buys them preferential access to behavioral control. So is anyone surprised that the rich have a preferential control, access and so on? Maybe not. And this is a tangent that might be, explored later, maybe in the discussion, whether the situation maps at all on actors that are actual entire agents in a society of agents, as opposed to being internal to a reinforcement learning scheme. Okay, so now that was an interim summary, and there are objections, and some of those objections are so potent that I cannot say that I at all times am convinced by my own arguments. This is speaking for myself. I don't want to speak for my co-authors in this case. I'm not entirely convinced at all times by my own arguments in particular in response to this first concern, which is why is it felt? Can the system pay the bidding cost without it hurting? So let me offer a couple of intuitions. So intuitively, an alarm, which is purely informational, augmented by hurting, would seem to be more effective than alarm alone. I mean, whatever hurting is, right? It clearly, we all know from experience that pain hurts. And knowing that something bad is about to happen or is happening and hurting for us seems to be more effective as a motivator and a cause for action. But despite this, so this is one piece of intuition, setting it aside, whether or not that's true, pain could have remained purely informational, but once the hurting aspect did evolve, it probably resulted in a stable equilibrium in the evolutionary landscape. And so now we are stuck in a situation, I mean, we could have been stuck in an equilibrium situation in which pain is just informational, but somehow we drifted or we jumped into a bad place to be, or maybe not, because pain, without pain, with pain asymbole, if you don't feel the pain, if you just know that something is wrong, you're really not in a good shape. Like evolutionarily, it's not a good place to be in. Anyway, there are analogs from animal behavior involving honest signaling. Specifically, one example that is mentioned in the paper is of nestling begging. You may know that in birds, the nestlings that share a nest in many species beg for food, and louder begging gives them more food. Of course, it may be costly, it likely is costly, because it takes up energy, and the whole evolutionary dynamic is in place here, which I actually have an opportunity to observe as we have a robin's nest above our entrance door right here. They just hatched a couple of days ago, so I can see the screaming. I can see the open wide mouths, and I can hear the screaming through the door, through the front door. Anyway, there is a discussion in evolutionary in zoology literature as to why the evolutionary dynamics of that kind of behavior ended up where it is. And one argument is to the effect that what I just proposed here, or I echoed that argument, saying that it could have been purely informational, but it was not, and now we are stuck in a valley in the evolutionary landscape. Now, a bit more to the point, what is hurting? What does it consist in? So what I would like to propose is that hurting is an inherent phenomenal aspect of the dynamics of certain computations. So we have two examples. The first one is the depletion of a homeostasis-related resource, which in itself, so if you have a resource like that being depleted, this in itself would make this process aversive, or the state aversive. And aversive means motivating energy expenditure in an attempt to escape it. So that's one example. If you're a system that is having its resource that is homeostasis related being depleted, you will hurt just by virtue of that. It's kind of an identity claim. Interestingly, the second identity claim, which has to do with specifically with our evolutionary proposal, the depletion of an action and context-specific resource, such as confidence of an actor in its bid to suspend aversion to present or projected state, would also hurt. And that's like the example with the brambles, and I'll persist and I'll push for the berries despite the pain from the thorns. So it's a different kind of pain. And after a long thought, which of course might have led me to a dead end, I'm very anxious to hear your comments on this. But it seems like those two types of pain, although they are independent for reasons which I mentioned, they cannot be one and the same, because they have their source, and the evolutionary reason for them is different. But nevertheless, they take the same form. There's a resource, which is being depleted, and this dynamic of depletion is hurting. That's what hurting consists in. That's what constitutes hurting. Now, I want to remark here that the various concepts here need to be defined. It's far from trivial task, need to be defined in computational dynamic terms, which are intrinsic to the system. So if you consider, say, some possession of mine as a resource, that's entirely beside the point. What I consider, what the system itself considers as a resource, not just considers as a resource, but is wired in such a way that if the resource is depleted, there are consequences which are unavoidable, which are obligatory, right? That's when the resource is a resource. How to formulate that in terms of, say, energy landscape, I don't know yet, but without such a formulation, which must be intrinsic to the system, it can be dictated from the outside. Without that, the word resource doesn't carry here a meaning which I intended to have. So to summarize that part, per aspera ad astra, that Latin saying, through the thorns or through the difficulties to the stars, and in the case of brambles and berries, this is literal. That's the slogan that summarizes this part of my presentation. So I think I have time for doing a bit more exploration. Yeah. So here it goes, 3 questions, and I'll start with the first one. Does an imposition of bidding cost on actors actually improve reinforcement learning? So the short answer is we don't know yet. Let me offer a very brief look at multi-objective reinforcement learning. So this clearly falls, the situation that I've been describing clearly falls under this rubric of multi-objective reinforcement learning, because in addition to the standard reward, positive or negative, there is something else here to consider, namely, according to our proposal, the confidence of the actors. So multi-objective reinforcement learning, this is a review from 2015, but more recent ones share the same view, is not such an exciting area. Sorry if you happen to be working in multi-objective reinforcement learning and you're excited by it. As an outsider, I find it kind of deflationary, because, of course, it has to be deflationary, because when you have multiple objectives in place, something needs to be done to bring them to a common denominator, so to speak. So you must combine somehow the different objectives, and it doesn't look like anyone has invented a way of getting multiple birds with the same stone in any sense. The standard consideration that is being invoked here is that of Pareto optimality, and you can't win in a big way here, but you can try not to lose by not adopting policies which are policies like C here. So F1 and F2 are 2 objectives. C is a policy which is dominated on each of the dimensions by other policies. So C definitely needs to be rejected. As to A and B, it's a different question. Should I choose A or should I choose B? There is no good choice. There's no good answer, no universal good answer. There's nothing to be done here. There is this notion of a Pareto front, which is the set of policies which are not dominated in a humiliating way. Like C is here, and different papers make different applications of this concept. Some of them are very sophisticated, and yet if you look at the list from this review, the list of approaches, the first one is the weighted sum, a linear weighted sum of Q values. So this concept from reinforcement learning is computed as the synthetic objective function. And what an outsider can say hearing this, of course you do a linear combination of objectives, and then you can pretend that you have one objective to optimize. And you go down the list, and there are no surprises here. And please correct me if I'm mistaken. If I miss something, I really would appreciate being set to right in regard to this area of multi-objective reinforcement learning. So I was really shaken by the title of this paper, which is very recent, I think from last year. And I thought, wow, they must have solved the problem of pain. Parallel reward and punishment controls in humans and robots. Safe reinforcement learning using the MaxPain algorithm. Well, you read the paper and this is the key part. So turns out they just call negative reward pain. It's true that they propose to separate positive from negative rewards. It's no longer on the same axis, positive, negative. It's positive reward, and orthogonally to it, it's negative reward, but then they do a linear combination, and it all kind of brings us to square one. And so pain here is not real pain. Thank goodness, because if you have a robot which you subject to real pain, at the very least, you should consult your institutional research board or oversight board before you do that. And I'll touch briefly upon this topic a bit later if I have time. So that's the reinforcement learning aspect. So I should say that I'm trying now to see if putting in place bidding, costly bidding on access to output actually improves performance over a plain reinforcement learning scheme. So maybe in a few months I'll have an answer coming from some simulations or some standard reinforcement learning tasks. So stay tuned. The second question for further exploration is maybe the most difficult one. What does pain consist in? So I keep returning to this question because again, as I shared with you, I don't think I have an answer that convinces me 100% of the time. Here, I can fall back on a couple of papers which have a common theme. This is our approach to phenomenality, the basic phenomenal awareness. So this is consciousness that is pre-self, that has to do just with awareness, which we believe is shared by many kinds of animals and much simpler or evolutionarily different ones from ourselves. Pretty much any animal with a sensor of the environment and of its internal state is capable of phenomenality on this account, on this definition of phenomenality. And the account which we proposed in two papers, one quite recent, this is the one on the top left here, the account equates phenomenality with a certain kind of intrinsic dynamics. So intrinsic dynamics is a bit of pleonasm because dynamics is always intrinsic to the system. This is what the system knows about itself and how it conducts itself. And I stress here is because this is a very strong claim and I want it to be very explicit for there to be no two interpretations of it. Phenomenality is a kind of intrinsic dynamic. So once you have that kind of intrinsic dynamic in place, you have phenomenality. Let me illustrate this with an example from one of my favorite pastimes, probably my most favorite pastime of all, which is hiking. What you see on the right is a map of a portion of Death Valley. There are two canyons here, the Marble Canyon here to the north and the Cottonwood Canyon to the south, south and east. The confluence is here. So it's a classic 3-day backpack in Death Valley. We actually did it with my first co-author, with Oren, a few years ago. We started here at the confluence, went up Cottonwood Canyon, up here to the saddle, and then down the Marble Canyon. And what I want to point out is that if you're here at the saddle, you can go down, all the way to the confluence by two distinct routes. You can go down the northern, the Marble Canyon route, or down the southern route, the Cottonwood Canyon. Those two routes are distinct intrinsically. It's not like I say that they are different. They are different because of the topography. The landscape in between here is kind of badlands, or at least for me, it's impassable. And so there is an intrinsic real difference between taking the northern route and the southern route. So imagine being at this place at the saddle. So I'm a system, this is my state, and something happens and I roll down, my state rolls down this path as opposed to that path. That's diagnosis, that's discernment, which is a key component, the central component of phenomenality. Any phenomenal state involves discernment, and the discernment has to be intrinsic to the system. It cannot be dictated from the outside. So if you have a system with dynamics which is trivial, like think of a piece of rock whose state space is kind of indiscriminate, it fills a volume, there is no distinction between one path through the state space and a different path, that is a system that is devoid of phenomenality. As opposed to a system which is like this, in some sense, in the critical sense, the intrinsic topology here is such that diagnosis, as in this, not that, by the system of its own dynamics is possible. So that's what phenomenality is. And in particular, in those papers, this work on the dynamical emergence theory of consciousness, we claim that distinct perceptual states correspond to coarse-grained macro states. In other words, it's a generating partition of the system state space, which means it's self-predictive. And the macro states, in this case, this example could be labeled like this: the start state, the saddle, this route through Marble Canyon, or this route through the Cottonwood Canyon to the confluence. And the distinction between Marble and Cottonwood here is not merely by some cartographer from the outside. Again, it's the topography inherent in the system's dynamics, the potential energy landscape, that defines the distinction. Here's Oren Kolodny, the first author, my co-author, temporarily defying gravity and kind of fighting the intrinsic potential energy landscape of that hike. This is in Marble Canyon. And as you can see, Oren can do wonders in terms of climbing up nearly vertical walls of marble for a while. So what we claim, taking this idea and applying it to the case of pain, what we claim is that pain is what the depletion dynamics of certain resources feels like. You can consider this illustration from a typical game, kind of a head-up display in a game, which lists the system's health, stamina, battery, whatever, number of missiles, whatever. The point is that a system in which those indicators of the depletion of resources are wired in a way that aversion is in place, and we claim bidding on excess, costly bidding on excess is in place, that system, just by virtue of that dynamics, will be experiencing pain. It's a strong claim, which again, I'm not entirely sure in, but I put it forward because I think any explanation of phenomenality, including pain, has to bite the bullet and make an identity claim of phenomenality with something. We choose the dynamics as described. Other theories choose other computational characterizations of the system's comportment. The information integration theory is one variety that comes to mind, and it would actually be an interesting exercise, far from trivial one, to connect the ideas from the information integration theory, which is all about the probabilities of states and transitions between states. Connect that to the dynamical picture that we keep in mind and try to think in terms of. And finally, the implications of our take on pain for engineering and AI. And this very short part, just a couple, maybe one slide, is based on two papers. This one, functional, effectively conscious, effective conscious AI, functionally effective, sorry, conscious AI without suffering, with Aman Agarwal, who was a graduate student here in computer science. So he got his PhD last year. That's the basis for essentially just the bottom line that I will offer you, because I'm running out of time, but that paper is kind of self-explanatory. It makes a connection between reinforcement learning on the one hand, and the concept of suffering as discussed by Thomas Metzinger. I mentioned him earlier, in particular looking at the possibilities of keeping reinforcement learning effective without yet bringing pain into the picture, right? So that idea, or that research direction, may be summarized by this quote from W.H. Auden, which we actually used as the epigraph for the pain paper, which I've been discussing today. Let me, instead of reading this, let me allow Auden himself speak these words.
But should you fail to keep your kingdom, and like your father before you, come where thought accuses and feeling mocks, believe your pain.
So honest signaling here offers a rule of thumb for ethics: believe pain. And with that, I conclude, and the only conclusion that meets the requirements in a talk about pain is fade to black.